show a radical. A radical, as you know, is a species that is having uh, an unpaired electron. And we will be doing the same thing. First thing we need to know if this radical is a delocalized system or not. And for that, we are going to assign hybridization to every single atom in the molecule. In this case, in the radical. Okay? Okay, so this carbon over here has a double bond, sp2 hybridized. The one next to it, same thing. This one on the bottom has all single bonds, therefore this must be an sp3 hybrid. Same as this one over here, double bond, sp2 hybridized. Now the next one here, this carbon has no pi bonds, once again 4 single bonds, 2 hydrogens and 2 carbons, so this must be an sp3 hybridized carbon. And the last two, obviously, will be sp2 hybridized since they share a double bond. So once we look at the molecule, we have properly assigned hybridization to every single atom, in this case all our carbon atoms. Well, there is one left, so this one over here, this is a radical carbon, and as I said, carbon, so carbocations, radicals on carbons, or carbon ions will always be sp2 hybridized. So when I look at my radical, I can tell I have 1, 2, 3, 4, 5 sp2 atoms next to one another properly aligned. The system is delocalized in this entire area. This double bond is isolated because next to it there is an sp3 hybridized carbon. So there can't be any delocalization in between here and here because there is an sp3 right in the middle. Okay, no p orbitals over here. Okay, for sp3 hybrid orbitals, no delocalization. Same thing applies here. This double bond here is isolated from this one because this carbon over here is sp3. It is connected through this one on top because this one will be sp2. So we have basically 1, 2, 3, 4, 5 carbons through which we will find electron delocalization. Now that we know that, let's draw the resonance structures to account for such delocalization. I'm going to put the double-headed arrow and then I'm going to add the brackets. So as you know already, now we're going to flow using the curve arrow symbolism. We're going to flow electrons from one structure to the next in order to generate resonance structures to account for the delocalization throughout these 5 carbons. Because it's a radical, and this is important, we are only, in this case, we will use a single-headed arrow, okay? So we don't use a regular arrow when you have radicals, okay? You use half arrow in that case. Unfortunately, according to the picture, I cannot have half an arrow here curved, which is gonna make my drawing difficult. I'm gonna try with this. So this I'm gonna try to see if I can do this better. No, okay, so this is a problem. Okay, this seems to be half an arrow, probably. Yeah, this is actually half an arrow. So we're gonna do, which maybe I don't know if I use it running because I couldn't see well. So this, let's assume this is half an arrow, okay? So in this case, we have one electron here, the unpaired electron. Sorry, and I use another one. So the unpaired electron is coming here, and one of the pi electrons is actually coming here. So meaning that one electron of the pi bond and this electron over here, I'm gonna move it to the, sorry, put in the resonance structures over here. So let's repeat the idea. And we're gonna flow the pi electrons now to generate resonance structures. Because it's a radical, we use an arrow with just one head, okay? Half an arrow, because we're indicating the flowing of one electron. So this one electron will be used for a pi bond here. And from this pi bond, one electron will be used to make this pi bond. So two electrons make a bond. Therefore, there will be a third electron that is going to be forming another radical. In this case, this one over here. Okay, so this will create a radical that in this case, so what I'm indicating by these arrows is the following. Okay, one electron from here and one from here to form a pi bond over here. And the second electron from the pi bond to form a radical on this carbon. So I'm going to move the radical over here. I'm going to add the double bond over here. Okay. Actually going to move that structure on the bottom, because that's make my structures flow better. And then I'm going to use now second resonance structures that I'm going to create by flowing the electrons toward the other side of the molecule. So I show the flowing on this side, now I'm going to show it toward this other side over here. So if I'm going to show the flow of electrons towards the right side of the molecule, once again, I'm going to take half an arrow, in this case, this one, to show that this electron, okay, is going to be forming a pi bond over here. And from the pi bond, one electron is going to be also forming or being used to make the double bond. Okay, so the unpaired electron used for the double bond pi bond here in this carbon-carbon bond, and one pi electron from the double bond will be also used for that. Therefore, from the double bond, one electron will be unpaired, forming a radical on this position. Okay, so we're going to draw the structure which is formed out of this localization. So once again, now the radical is indicating to be forming this carbon over here. The double bond I showed that will be formed over here. The other double bond remains the same because I didn't touch it. And that's pretty much it. Why is that? Because if we look at it, I'm going to expand this. Sorry. So once again, the radical was in this position. We showed the localization toward this side. Radical comes over here. And then if you ask your question, can I draw another resonance structure? Well, no, because in the carbon next to it is sp3 hybridized. Remember, this is an isolated double bond. And the delocalization in this section is already shown over here. Same thing happened to the other side. The delocalization in this section, these three, is shown over here. This radical cannot be delocalized toward this side because this carbon is sp3. So the real structure of this radical is a radical in which the carbons having radical character are this one, and this one. A carbon with a radical, guys, is a carbon that has actually 7 electrons in the valence shell. So that carbon, and I'm going to redraw now the hybrid. Again, I don't have the capability of drawing the partial charges over here, but I can show without happen. So once again, a radical is an electron deficient, okay? Meaning that the carbon-bearing radical has 7 electrons in the valence shell. It will accept another radical, another electron to form a bond, completing 8 electrons in the valence shell. So if we were to think about the real structure of this radical, as I said, the character is sharing between this carbon, this carbon, and this carbon. In the rest, we will have, as you know now, partial double bond character. So because this is a radical that is electron deficient, it will react with another species, I just said right now, in this case having also an unpaired electron. That way it can form a bond. So if another radical approaches radical, it will attach either to this carbon, or to this carbon. That's the data you can interpret out of this resonance structure, okay? So I'm going to summarize now this second part. So we look at this structure. We quickly saw that this was a radical carbon. Remember, it's a carbon with 7 electrons in the valence shell, is neutral, okay? And sp2 hybridized. First thing we did, assign hybridization. We found that we have 1, 2, 3, 5 carbons that are sp2 next to each other, properly aligned, so there is delocalization in this entire area of the molecule. We show this delocalization by means of the curved arrow symbolism. In this case, because it's a radical, we use only half an arrow. So half an arrow to indicate that this radical can delocalize toward this side to form a pi bond with 1 electron from the next pi bond, forming a pi bond over here. Obviously, the extra electron of the pi bond will be in this carbon. And the same thing toward this side. Delocalize toward this side, forming a pi bond on here. The radical will be in the carbon, forming that previous pi bond. No more delocalization toward this side because there is an sp3. No more toward this side because there is an sp3. When we read this data, we see that in this radical, there is delocalization. The single electron, so this unpaired electron is delocalized toward this area. That's what it means. This electron is delocalized, and the highest electron density with this electron will be in this carbon, on this carbon, and on this carbon. That's what the resonance structures are telling you. Therefore, radicals react with some other radicals to complete a bond. So if another radical approaches this one, it will bind either this position, or this position, because those are the 3 positions that share the unpaired electron of this radical, according to resonance theory. Okay? Hope you guys understood. Just to make sure, because I don't want this to be confused, I believe I made a little mistake. I did not intend to use a single arrow. I'm gonna just change it just in case. Okay? Because I didn't, it was my site is getting bad and I didn't realize. So I just want to make sure that everybody understands that this arrow indicates 2 electrons, is a full arrow here. Okay? And the one below indicates the flow of 1 electron because that was a radical. Okay? So I'm just gonna fix this just in case somebody is confused. So if you have carbocations or carbon ions, always use a full arrow because you're flowing 2 electrons from pi bonds along pairs. If you have radicals, always use half an arrow because you're indicating the flowing of just 1 electron. I cannot emphasize enough, okay? You talk about energy of resonance structures, significant contributors. You never mention that resonance structures are stable because remember, none of these structures exist. The real thing is just a hybrid of all of them. So guys, I hope you understood this video and it helps you to solve the problems in the homework. And more than that, any problems that you faced in the future regarding resonance. One of the most important skills in this class is to have a methodology of thinking. That means whenever you see from now on a resonance problems, you're going to follow this step. You're going to identify, once again, hybridization, the localization area, and then you will show the resonance structure. If you follow that pattern, it will be very unlikely that you will make a mistake in the question. Okay? I hope you guys enjoyed the video. And if you have any questions, just please feel free to ask in the class or in office hours. Okay? Bye.